Welcome everybody. Today we're going to be starting chapter 11 and we're going to be looking at colligative properties. So this is really just an intro to colligative properties. We're going to be looking at the freezing point depression as it is relatively straightforward, and further colligative properties will behave very similarly. As we lead into colligative properties, we're going to review how things dissolve, which is so fundamental to this and really worth taking a close look at if you don't remember very well. All right, so here we're taking a look at chapter 11, where the focus is going to be on solubility and colligative properties. And colligative properties is what we're going to introduce in this video. And to review, it's really important that we remember how things dissolve. And this is to say soluble ionic compounds versus soluble molecular compounds. And so we have two equations that are here. Both of these show putting species into water. So we have potassium chloride, KCl, in the solid state that's going to dissolve in water, and pure liquid ethanol put into water to become solvated aqueous ethanol. And note that we have a different looking chemical equation for both of these, right? We have KCl becoming K plus and Cl minus, and that looks sort of like the following. We have this solid block of KCl that's shown in the bottom of the picture, which as it encounters water, breaks apart and really becomes positive and negatively charged ions, K plus and Cl minus. In contrast, ethanol simply solvates. We have ethanol molecules that will form new interactions with water, but there is no breaking apart of the ethanol structure. It simply dissolves, it does not dissociate. And so we can look at this and see, well, ethanol in water still maintains that structure, whereas KCl breaks down into individual ions. And this introduces the idea of electrolytic species, where because of the dissociation, not just dissolution, but dissociation of the soluble ionic compound KCl, we end up having an ability to conduct electricity, whereas ethanol, we don't. But very much importantly here, when we have a single KCl, one potassium and one chloride, it's going to become two different chemical species, a single K plus and a single Cl minus. One thing breaks up into two, whereas with ethanol, we simply have the ethanol become solvated. There is no breaking up. Okay, that's really important to know because colligative properties are ones where the effect of the solute is going to change the properties of the pure solvent. And it's going to be in accordance with how many particles there are. Colligative properties aren't going to care about if the particles are larger or smaller or positive or negative. It's only going to care about how many there are. And that idea of K plus turning into, or the idea of KCl turning into K plus and Cl minus is going to matter a lot. And so let's consider first what happens when we salt an icy road. So we know that salting removes the ice, but why does it remove the ice? And, maybe consider pausing here for a second and hypothesizing why this is, and then we'll continue. All right, salting removes ice. Why is this? Well, it's because the addition of solute inhibits the ice formation. And so this is our colligative property, where we have the addition of something to pure water that breaks down the ability to form ice. And because that ability is inhibited, it needs to be colder for the ice to form, meaning that if we're at the same temperature, kind of borderline, the ice will melt. And so this is calculated in accordance with the following equation for freezing point depression. Delta TF is the depression of the freezing point in degrees Celsius, how many degrees we bring the freezing point down. Kf is a freezing point depression constant that is an identity of the solvent, which in this case is water, the ice. That's what we're looking at, is we're looking at the solvent and how things change with that. And the M here, script M, is the molal concentration, meaning molality. And very importantly, this is not molarity. Molality is defined as the moles of solute per kilograms of solvent, and many colligative properties will deal with molality rather than molarity. Important to be able to keep track of that. Okay, so let's look at an example problem. Here we have 50 grams of sugar added to 1 liter of pure water, and I've added a few definitions and things for you. So I recommend you pause, see if you can solve this one with what's given, and then I will show you my solution. All right, so here we have 50 grams of sugar. We're putting it into water. The steps that we do to solve for this one will be first, let's note the freezing point of water is 0 Celsius. And this is going to matter because we're solving for the freezing point depression. This delta TF that we solve for is going to be a depression from 0 Celsius. We can get the value of Kf out of OpenStax. It's an 11.2, and this is 1.86 degrees Celsius per mole-al. Next, we need the mole-al concentration, and from there, it's pretty much just however many molalities we should have will depress the freezing point by 1.86 degrees Celsius. That's what it shows. So we find out the moles of the solute, that's the sugar, 1.46 moles of sugar. We know the solvent here is 1 kilogram because we know it's 1 liter, and the density of water is 1 milligram per milliliter, also known as 1 kilogram per liter, and therefore we have 0.0146 mole-al. We plug it in, we see that the freezing point depression is 0.271 degrees Celsius, and therefore the freezing point is lowered by 0.271. We're almost done. We need to actually state the new freezing point. This is freezing point depression, and our new freezing point will be negative 0.271 degrees Celsius. It only lowers the freezing point. It does not raise it. That is how this particular colligative property works, freezing point depression. Okay, what if we use 50 grams of sodium chloride instead? So go ahead and pause here again and see if you can calculate the freezing point for water if instead of using 50 grams of sugar, we use 50 grams of sodium chloride. And as a hint here, that thing we talked about in the beginning about the dissociation will be very important here. How do we account for that? All right, so now that we are looking at salt instead, sodium chloride, we need to think about how many ions are formed. So here, 2 ions are formed. We have to multiply the molality by 2 because for every 1 mole, 1 mole-al of our solution, we actually get 2 mole-al of ions. And so first, let's get the moles of the sodium chloride. We calculate that, and we know that this is going to be 0.856 mole-al sodium chloride. But we know that each of these sodium chlorides breaks into 2 pieces. It dissociates completely, and so the total ion molality is going to be this value doubled, 1.71 for total ion molality. And that's the value that we want to use here. Same Kf, still water, and the freezing point depression is 3.18 degrees Celsius. And so is this the answer we should report? The new freezing point is 3.18? Not exactly. It's going to be 3.18 lower. We know the freezing point of water is 0 Celsius, so our new freezing point is negative 3.18 degrees Celsius. Same amount, seems to work much better than sugar, not only because of the lower molar mass, so there's more moles of the sodium chloride in the 50 grams, but also because of this dissociation. Okay, so the way we tracked it previously is a little bit cumbersome, and the way that we can do it a bit more straightforwardly is through the Van Hoff factor I. And here we've adjusted our equation somewhat to roll that I into our freezing point depression calculation. Here, the Van Hoff factor is assigned to our solute, which is the sodium chloride. It's the effective number of particles per solute, per formula unit of solute. And so, sodium chloride, we know that it breaks into sodium chloride, and so this idea of 2 is a really good place to start. This is theoretically what happens if they all dissociate. But in reality, this isn't quite what happens because we still have some that are glummed together. So here's potassium chloride, behaves very much the same. Most of them dissociate, but there are a few ion pairs that are left behind. It's not a perfect world. The water does not break apart every single one of this, 1 mole, 2 moles, however many, on the order of 10 to the 23 pairs. There are a few that get missed and just aren't solvated by the water. And so because of this, we can kind of start to think about the Van Hoff factor in a theoretical way as well as a practical way. So here, I equals 2 would mean perfect 100% dissolution, and real solutions are not that perfect. And so here we have a difference between the measured and the predicted Van Hoff factor. Again, I is this Van Hoff factor. This says how many particles are created when we dissolve 1 particle. And up at the top we have our sugar-like thing. Here's glucose. It's non-electrolytic. It doesn't dissociate. It remains the same when it's solvated. That's I equals 1, and that's what we see. And then what we see here for things like sodium chloride or hydrochloric acid, which are strong electrolytes, is that while we expect 2 particles to form, in reality, it's somewhat less, 1.9, right? We have a few that are not quite getting all the way there, right? Because remember that a full 2 is perfect dissolution. So again, putting this out there is really useful because it shows, the differences between what we predict and what we measure. And again, chemistry is all about measurement. The way we get the measured Van Hoff factor is through actually calculating the new freezing point and saying, well, if this is the new freezing point that we get, it must have gotten to that point through making this many particles, and we can calculate I that way.